Hello everyone and welcome to this session. It's for the third secondary year General Sciences section. This is a math chapter in which we are going to introduce a new counting technique, the combination. At the end of this chapter, you will be able to find the number of combinations of n elements taking p at a time, apply the binomial formula of Newton, and use the combination in problem solving. But first of all, let's start by reviewing few counting techniques that you took before. Fundamental counting principle. A small deli offers 4 types of meat: chicken, turkey, beef, and fish, and 3 types of bread: white, brown, and dry. List all the choices that the customers have for a meat sandwich. Notice that the number of options here is a small number, so you can solve the problem by using a tree. Let's start by listing the options available for meat. I have C, T, B, and F. If you choose chicken, you will have 3 different options for the bread, which will give you 3 different sandwiches: CW, CBR, and CR. If you continue using the same technique, you will get all available options for sandwiches, which is a total number of 12 choices. 4 comes from the options available for meat and 3 comes from the options available for bread. In the second activity, we have a class formed by 25 students. Out of them, 16 play basketball, 11 play football, and 4 don't exercise any sport. Complete the Venn diagram. What is a Venn diagram? We have a rectangle for the whole class. The blue oval is for students who play basketball and the red oval is for students who play football. This space in between, the common space, is for students who practice both sports. I know that 4 students don't exercise, so I'm going to put 4 over here, which will give me 21 students who play. So I have 16 students who play basketball, 11 who play football, which gives a total of 27. So there must be a specific number of students who practice both games. So let X be the number of students who practice both games. To know the number of students who practice basketball only, I need to exclude the ones who also play football, which will give me 16 minus X. Similarly, the number of students who play football only is 11 minus X. And now, in order to solve this problem, I must find X. I know that the total number of students is 25, so I can form a first degree equation by adding all the numbers in the diagram. And by solving this equation, I get X equals 6. So the diagram will be like this. I have 6 students who practice both games, 10 who practice basketball only, 5 who practice football only, and 4 students who don't exercise. This is the Venn diagram. In this activity, we need to find the number of words of 3 different letters that can be formed out of the letters A, B, C, D, and E. I want you to notice the word different. Why is this word important? Since it tells that every letter should only be used once, so no letters should be repeated in any of the words. In other words, it means if you use one of the letters in the first place, this letter must not be repeated, so you will be left with 4 options for the second place and then 3 options for the third place. Which means 5 times 4 times 3 equals 60 different words. In number 2, list all the words formed by the letters B, C, and E. Since I have 3 letters only, so I can use the tree method. If I start with the letter B, I can put C or E in the second place, and then if I use B and C, I will be left with E. In this way, I will have 6 different options. So the number of these words is 3 times 2 times 1 equals 3 factorial, which is 6. And what is the factorial of a natural number n? The factorial of a natural number n is the product of all natural numbers starting from 1 up till n. This is how we get 6 different words formed by the letters B, C, and E. Now this is an activity related to the previous activities we solved. A, B, C, D, and E are 5 points on a circle, as shown in the figure. The question is, how many triangles can be formed out of these points? Notice the drawn triangle over here, DCB. This triangle will not change if I name it DBC or CDB as long as I'm naming the same vertices. so 3 different points can form one triangle only. Unlike the case of words, to form a word, the order is important. So the word DCB and the word CDB are 2 different words. This is why we got 6 different words formed by 3 different letters. But in the case of a triangle, 3 different points can form one triangle only. This is why to find the total number of triangles, I'm going to use the number of words we found in the previous activity, and I will divide it by the number of repeated words, the words formed by the same letter, which is 3 factorial as calculated before, which will give me 60 over 6 equals 10. This is how I avoid the repetition of the same triangle among the options. To verify this result, I can trace the triangles. So I can fix one of the sides. Here I'm going to fix side DC and change the third vertex. I will have triangle DCA and triangle DCE. I can do the same thing by fixing the other side DE or EA until I get all the triangles that are found in this figure. Definitions. The number of permutations without repetition of n objects taken k at a time is npk equals n factorial over n minus k factorial. N is the total number of items and k is the number of items we're considering. A combination is a selection of some or all of a number of different objects. So I'm selecting a specific number of objects, and in this selection the order has no importance, just like the example of triangles we saw previously. We express combinations in different forms. It is denoted by one of these forms. You can choose any one of them as long as you make sure you're placing k and n in their correct places. N refers to the total number of items and k refers to the number of items we're selecting. This combination is equal to n factorial over k factorial into n minus k factorial. Some rules of calculation of combinations. C0n is equal to Cnn is equal to 1. So if I'm selecting nothing or I'm selecting all items, I get 1. Ckn is equal to Cn minus kn is equal to n factorial over k factorial into n minus k factorial. To prove this equality, you can refer to the definition of combinations and replace k by n minus k. Simplify, it will give you the same answer. Another identity that's very useful in exercises, Ckn is equal to Ckn minus 1 plus Ck minus 1 n minus 1. To prove this equality, you can assign specific values for n and k and use your calculator to calculate the combinations. Example: a committee of 4 persons, president, vice president, treasurer, and secretary, is to be selected out of a group of 10 students. In how many ways can this be done? Notice that in this problem, every person in the committee has a specific role, so the order over here is important. I have 10 options for the president, and if I select a president, there will remain 9 options for the vice president, and so on, 8 options for the treasurer, and 7 options for the secretary, which will give me a total of 5040 possible committees. Remember that in this case, every person has an assigned role. The total number of committees will be 5040. To avoid any discrimination, the 10 students in the council decide to select a 4-member committee where the order has no importance. And why is that? Because no roles are assigned, so all members are the same. In how many ways can this be done? So I have to remove the repeated committees with the same person. When the order is important, the total number was 5040 as calculated previously, but now since the order is no more important, so each group of 4 will form one committee with no assigned roles. I need to divide by the number of repetitions, which will give me 120 possible committees. This number is equal to the number of combinations of 10 students taken 4 at a time, so it's equal to C410 because I'm selecting 4 students randomly without assigning any role for any of the students. The binomial formula of Newton. Let's read this formula together. a plus b exponent n is equal to c0n a exponent n plus c1n a exponent n minus 1 b plus c2n a exponent n minus 2 b squared, etc. until we have cnn b exponent n. Notice the terms of this formula. Each term is formed with three different factors. The first factor is a combination starting from c0n until cnn in the last term. And then I have factors that are powers of a. We start with the power a exponent n, and the powers start to decrease their exponents by 1 until we reach a exponent 0 in the last term. Similarly, we have the powers of b, where b is the second term in the binomial, starting with b exponent 0, and the exponents will start to increase by 1 until we reach b exponent n in the last term. We can verify this formula by using the remarkable identities. Let's verify it for a plus b squared. I have a squared plus 2ab plus b squared. Let's compare a plus b squared to the binomial formula of Newton. I have n equals 2, so I'm going to replace n by 2 in the above formula. Over here we will have c0 taken from 2, which is equal to 1, and notice that the coefficients of the first terms and the last terms are always 1. And why is that? We can refer to the rule we learned before. C0n and cnn are always equal to 1. And I can continue this formula by replacing n by 2. Similarly, in a plus b cubed, I have the same formula applied when n equals 3. So I want you to notice one important thing over here. Coefficients of the second and the third term are the same. And why is that? Since over here I have c1 from 3 and c2 from 3, which are equal based on the previous rule we learned. ckn is equal to cn minus kn. This is an application on it. They will both give 3. And notice the decreasing exponents of a and then the increasing exponents of b. You can apply directly by replacing n by 3 in the above formula. And it works for any binomial of this form. Let's do some examples together. Find the coefficient of x cubed in the expansion of 2x plus 3 exponent 7. Notice that we can use the binomial formula of Newton, where a is equal to 2x, b is equal to 3, and n is equal to 7. Also notice that 2x is the first term in this binomial, which means the exponents of 2x must be decreasing. So x exponent to 3 will appear when n is equal to 7 and k is equal to 4. This is why the coefficient of x cubed in this expression will be c of 4 taken from 7 multiplied by 2 exponent to 3, where 3 comes from 7 minus 4, multiplied by 3 exponent 4. Notice that I excluded x cubed because I need its coefficient only. I don't need the whole term. You can use a calculator to find the final answer. Another example, we have to simplify 1 plus c1n 3 plus c2n 3 squared and so on. We can compare this to the expanded form of the binomial of Newton. We get that a is equal to 1 and b is equal to 3. Let's replace it in the binomial form. I have 1 plus 3 exponent n, which gives 4 exponent n. Now some applications on our chapter. A bag contains 5 red balls and 7 green balls. 4 balls are selected randomly and simultaneously from this bag. When you see the word simultaneously, it means we have a combination because we're selecting a specific number of items out of a total number of items that are contained in a bag. These are the balls. In how many ways can this be done? So since this is a combination, I have to be selecting 4 items, but out of which total, how many balls are there in the bag? I have 12 balls. So the number of possible ways of selecting 4 out of them is a combination of 4 items out of 12. C for 12 or 12 choose 4. If you want to calculate the number of outcomes of the following events, starting with the event 4 selected balls are red, my total number of items that are accepted is now 5 instead of 12, so it will be a combination of 4 out of 5. More examples. In the event, the 4 selected balls have the same color. So here I have 2 options. The 4 balls might be red and the 4 balls might also be green. So I have 2 different types of outcomes that are accepted. The number of outcomes for this event will be C4 taken from 5. This refers to the red balls, and C4 taken from 7, it's a combination of 4 green balls. And I add them since these 2 different outcomes are not connected. In the event C, the 4 selected balls are 1 red and 3 greens. Over here, I have 2 different conditions in a same outcome. So one outcome must include a red ball and 3 green balls. It's also a combination, so I'm selecting 1 ball out of 5 for the red and 3 balls out of 7 for the green, and I'm multiplying since the 2 conditions refer to one outcome. In the previous event, these were 2 different outcomes, this is why I had to add, but over here, since they represent the same outcome, so I need to multiply. The 2 conditions must be satisfied at the same time. Exercise 4. A box contains 11 cards numbered 1 through 11. 3 cards are randomly selected at one time from the box, so here I have the word one time, that stands for simultaneously. It's also a combination. The question is, in how many ways can this be done? So if I'm selecting 3 cards out of these 11 cards, it's a combination of 3 items out of 11. So 11 items taken 3 at a time is a combination. We can use the calculator to find the final answer. Calculate the number of outcomes of the following events. The first event, the 3 selected cards have even numbers. So notice that 5 of the given cards have even numbers, so my selection now will be 3 cards out of 5 holding even numbers, so it's a combination of 3 taken from 5. With the same cards, we have the event B, exactly 2 cards have even numbers. Since 2 of the selected cards must have even numbers, then the third card must have an odd number. So I will be selecting a combination of any 2 cards out of the even numbers, which are 5, and 1 card only from the odd numbers, which are 6 cards. It will be a combination of 2 out of 5 for the even cards and a combination of 1 out of 6 for the odd cards, and it's a multiplication again since the 2 conditions refer to the same outcome. Event C, at least 1 card has a multiple of 3. Since I have different multiples of 3 among the cards, it's easier for me if I find the complement of this event, which is C bar, no card is a multiple of 3. If I don't want any multiple of 3, I will be left with 8 cards and I will be selecting 3 cards out of them, so it's a combination of 3 cards out of 8, which are the cards not holding a multiple of 3. And now, to find the number of outcomes for the event C, I find the difference between the total number of outcomes of this example, which is 3 out of 11 cards, and I subtract the number of outcomes of the complement of the event C, which will give me the number of outcomes for the event C. Event D, the 2 cards numbered 2 and 5 cannot be together in the selection. Also in this case, it's easier to find the complement of this event where the 2 cards appear together in a selection. So D bar, the 2 cards numbered 2 and 5 are together in the selection. Now that I know that I need 2 and 5 to be appearing, the choice will be left for the third card to be any of the other cards. So I will have 9 outcomes for the event D bar, in which I'm fixing 2 and 5 and I'm only changing the third card. And also, to find the number of outcomes for the event D, I will be subtracting the total number of outcomes of this experiment minus the number of outcomes of D bar. And you can always use your calculator to find the final answer. Event E, 2 cards have even numbers and 1 card has a multiple of 3. You have to be careful over here because the card number 6 is even and also is a multiple of 3. So we have 2 different options. In the first option, if the multiple of 3 that is selected was the card number 6, I will need another even card, And I will also need a card that is not a multiple of 3. So I will select the card number 6, which is even and a multiple of 3, and I will select another even card with a card that is not a multiple of 3 and that is odd, so that I'm verifying all conditions of the event. So I will have number of outcomes that is equal to 1, this is for the card number 6, and 4, this is for the 4 different choices of one card among the even cards, and this is for the 4 different choices of odd cards that are not multiple of 3, which will give me a total of 16 outcomes. The second option is if the multiple of 3 that is selected was not 6. So if the multiple of 3 is not 6, I need 2 different even cards that are not 6, and I will also need one odd card that holds a multiple of 3. So I will select a card between 3 and 9, which is a multiple of 3 other than 6, and I will select 2 cards from the even cards that are not 6. To verify all conditions, I will have 2. This 2 comes from the choice between 3 and 9. You can also write C of 1 taken from 2 multiplied by a combination of 2 even cards taken from 4 cards. It will give you a total of 12. Now for the number of outcomes of the event E, I have to add the possibilities obtained from option 1 and the possibilities obtained from option 2. That will give me a total of 28 possible outcomes. These are the examples that we want to solve together. You can do more exercises found in your book. Thank you for your attention and stay safe.